Okay, so welcome everyone to the Australian Geometric PDE seminar. Today we have James Stanfield from UQ, and he'll be speaking on Hermitian manifolds with flat Gauduchon connections, which is one of his recent works with Ramiro. Take it away, James.
All right, thanks, Kyle. It's saying my internet connection's unstable, but everyone's okay, they can hear me. Okay, excellent. All right, well, thanks for having me. Thanks for the invitation to talk. I'm very excited to present this finally now finished project. Yeah, so as Kyle mentioned, this is joint work with Ramiro Lafuente, who unfortunately can't be here today, but so we're looking at a problem in Hermitian geometry. Okay, so I'll start with a setup. I'm not going to assume everyone here is super familiar with complex geometry or anything, so I'll start fairly simple, and please ask any questions that you want. I'm happy to answer whatever. Okay, so yeah, let's start with the setup. So I've got M, J, and G. This is a Hermitian manifold. Okay, so that is, for those who don't know, okay, this is the pair M and J is a complex manifold. All right, so again, this means the following. M is just a smooth manifold. In fact, it will be real analytic by Newlander Nuremberg. So M is a smooth manifold a priori, and then we have some endomorphism. J. Okay, so this maps tangent space to tangent space. It's just think of it as a matrix if you want. And it squares 2 minus the identity. Okay, so this plays the role of a complex structure. It's not quite a complex structure. We need it to play well with the smooth structure. It needs to satisfy this certain integrability condition. Okay, the easiest way to write that condition would be that this bundle is involutive, right? Where this bundle is just the plus I eigenbundle of J, considered as a map on the complexification of our tangent space. So technical integrability condition, all of this basically makes it equivalent to having a holomorphic axis, to the existence of a holomorphic axis, atlas. Okay, so you have maps into the complex, C to the N, and the transition charts are, well, you have charts into the Cn, and then the transition maps are holomorphic. Okay, so that's the first 2 bits of data. The last bit of data is a emission metric. Okay, so this is just a Riemannian metric. Okay, and for this metric, we just want J to be a linear isometry. Okay, so we want multiplying by I to not change lengths or angles of vectors. Okay, so one point I want to make is that these always exist on a given complex manifold. Okay, you do some argument with a partition of unity, right? And you can construct any Hermitian metric on your complex manifold. So it's nice to have that to be able to study these things. So I'll just make a definition. The nicest kind of Hermitian metrics are what we call Kähler metrics. So G is called Kähler if the complex structure is parallel with respect to the Levi-Civita connection. I'll just make that. And if you like, this is equivalent to this form omega being closed, where omega is what we call the fundamental form or the Kähler form. This is just G that's been twisted by J. Okay, and we ask that that form is closed. Okay, if your Riemannian geometry is rusty, right? So recall that the Levi-Civita connection, okay, it's a connection, right? So it's a directional derivative, so to speak. It's the unique one for which the metric is parallel and it's symmetric. And by symmetric, I mean it has zero torsion, or this is satisfied. Okay, and that's the unique metric for which that holds. And this is the unique connection for which that holds, and this is the connection behind Riemannian geometry. So the Kähler picture looks like this. Say I have a vector. Okay, I can multiply by I, effectively multiplying by J, and this gives me another vector. And the Hermitian condition means I want this to be a right angle. Okay, as in I want it to be orthogonal. And the Kähler condition means if I parallel transport along some curve, then this multiplication by I commutes with this parallel transport. So these are somehow the nicest Hermitian metrics. Okay, but there's a problem, right? Hermitian metrics, they always exist. Again, use this partition of unity argument, but Kähler metrics are topologically obstructed. In saying that, I should probably let you know there are examples of these Kähler metrics, right? So there's the complex projective space with what we call the Fabini-Strudi metric. Okay, and any projective manifold. By that I mean some submanifold of CPM. Okay, because you can just restrict a Kähler metric to obtain a new one. So they do exist an abundance of examples, but not so abundant. So they're topologically obstructed. For example, the first Betti number, no, not the first Betti number, sorry, all the odd Betti numbers are even. Again, this comes from Hodge theory. Okay, and so immediately there's also an abundance of examples with no Kähler metrics, right? So for example, one of my favorite manifolds is the Hopf surface. I guess there are many of them. So I guess for those who have done a little bit of, for example, did the UQ course in Riemannian geometry, they're probably familiar with a similar kind of construction. If you fix some complex number lambda and you demand that its norm is between 0 and 1, then there's an action of the integers on, say, the plane, the complex plane, well, C2 minus the origin. Okay, and this action takes some vector, and we just do lambda to the n times that vector. Okay, and then we can define a complex manifold. So this action is free, it's properly discontinuous, so it's quotient. The quotient manifold, well, the quotient space is indeed a manifold, and it's diffeomorphic to S1 cross S3. It's a nice exercise to actually try and construct this diffeomorphism. Okay, so why am I doing all this? Well, I mean, it's not too hard to work out the Betti numbers of spheres and the Betti numbers of products. This is just one. So that means it has no Kähler metrics. I like doing this example because it's something I didn't see until embarrassingly late. Yeah, and there's most complex manifolds won't be Kähler. I'm sure you could make that sentence precise, but I'm not quite sure at this current instant. But anyway, that's my point. There are plenty of complex manifolds with no Kähler metrics. Are there any questions on the basics so far? Hopefully I haven't cut out or anything. Okay. Might as well start a new page. So my point is that we really need to, you know, Kähler geometry is beautiful, but we really need to broaden our scope to consider other geometries, right? So if G is non-Kähler, we need to consider better connections, right? So I'm going to call these emission connections. Okay, so recall that Kähler is just defined by the complex structure of the Levi-Civita connection being parallel. And if it's non-Kähler, well, then we lose this. So now the Levi-Civita connection is a pretty terrible connection for non-Kähler emission geometry. Okay, so we need to look at connections perhaps by dropping this condition, right, allowing them to have torsion, but for which they are parallel with respect, or for which J is parallel with respect to them. Okay, so I'm going to define this space as H. This is connections nabla such that, well, they are Riemannian in the sense that G is parallel and J is also parallel. Okay. So in general, this is, you know, this doesn't nail down the connection quite like the conditions for the Levi-Civita connection does. This is actually an infinite dimensional affine space. Okay, so it's modeled on some tensor space. The difference between any of these two connections is some tensor. And you know, because this manifold, you know, for a non-Kähler, generic, should say maybe generic connections in H have torsion. Right, and what do I mean by that? Well, I'll just define it to be this tensor. So this is the kind of the first order invariant of the connection. Okay, and this generally is non-zero for these connections, unless the manifold is Kähler, in which case there's one emission connection with non-zero torsion, with zero torsion. Okay, so we want to broaden ourselves to non-Kähler geometries. We choose a connection in here. It's a wild space, right? It's an infinite dimensional space. And we want to generalize Kähler geometry. So we want to choose connections which will agree with the Levi-Civita connection in the Kähler case, okay? In general, even in the Kähler case, this is still infinite dimensional. These don't collapse to a point. So it's natural to kind of look for a subspace of H that will generalize the Levi-Civita connection. So a subspace that collapses to a point in the Kähler case, but is not a point in the non-Kähler case and is still Hermitian, right? So the work of Gauduchon covered this in the 90s. So this is some ideas of Gauduchon in 97. Okay, so how do we pick the best connections from this space, right? Well, we use dark magic, otherwise known as representation theory. Okay, so there's a natural action, right, of UN acting on the space of torsion tensors, right? So, you know, torsion tensors, they eat two vectors and they spit out another vector, right? So this would be vector valued two forms. Okay, and UN acts on them, right? So these are the torsion tensors. Why? From the metric, so we have a group ON, and then the complex structure J means there's a UN sitting inside that ON acting, okay? And now you can ask, what are the irreducible submodules of this, okay? And then we could decompose elements of this vector space into the irreducible components, okay? So we add some rep theory. Okay, and eventually this leads to a line of Hermitian connections. Okay, sort of this canonical line of connections sitting in H. So I'm going to call this H sub G for Gauduchon. Okay, and this is well, it's a line, right? So it's a one-dimensional space. We have this nabla S. So S is the affine parameter, and we define our connections like this. So it's just some combination of two other connections, and I haven't defined these yet, but I will. And this is truly a line in our space of connections, okay? And the point is that G is scalar if and only if this space is a point. Okay. So any connection in here would be a valid geometry which generalizes Taylor geometry. Okay, so these are all valid generalizations. I'm just repeating myself, but yeah, this line is kind of what generalizes scalar geometry. Okay, I should define the rest of this. So this nabla C, which is up here, okay, this is part of the line. This is called the Churn connection. Okay, and it's characterized, it's the unique connection such that its torsion satisfies this. So we have this torsion tensor, and basically we say we can pull out J. Okay, and if you prefer to work in sort of complex coordinates, what this means is that the kind of I, J bar part of the torsion is 0. Okay, so all the information of the torsion is carried in components that look like that, and they're conjugates. Okay. So this is kind of the most common connection that people have used historically. But there are other valid ones, right? So for example, you know, the Churn connection, it's quite nice, right? The first Chern-Ricci form, which is kind of the Ricci curvature of this connection, it's cohomological. So, you know, it's had, you know, quite a lot of interest and success, right? But another connection that is perhaps less famous, but also equally fascinating, is the Bismut connection, and is sometimes called the Strominger connection. Okay, so this is characterized. So this is the unique connection such that such that T, so it's torsion when we contract, right? So we bring down an index, so to speak, and we have this this 3 tensor. Okay. Well, we ask this to be a 3 form. Okay, so we ask this tensor to be totally skew symmetric. Now, a torsion tensor is already skew in these two components, right? So generally speaking, for any connection, T of xy is always minus T of yx. Okay, but it's not necessarily skew in these two. And the Bismut connection is the kind of unique connection in H such that this is satisfied. To be super precise, I probably want to say the unique connection that is Hermitian, right? So unique connection in H on both of these. Okay, so we want it to be totally skew symmetric, a 3 form. You know, this has come up quite a lot in, so the reason the name Strominger, you know, it comes up in non-Kähler Calabi-Yau stuff and some string theory and stuff. I don't know enough about it to talk on it too much, And Bismut has used it to prove some index theories on non-Kähler manifolds. So the Bismut connection has actually been quite powerful. It's also used in pluriclosed geometry. For example, the pluriclosed flow is just the evolution of the it's like the Ricci flow, but we've replaced Ricci by the first Ricci of the Bismut connection, right? So this kind of replaces the Levi-Civita connection for the pluriclosed flow, which is quite interesting. So these are two distinguished connections in this line. So far, well, maybe before I go on, I should ask if there's any questions again. Oh, I've got a question in the chat. Oh, no question, a statement. Yeah, cool. Good point. So what was I saying? Okay, so we have this line. And basically the way I've justified it so far is to say,
James, maybe it's worth mentioning exactly why there are first, second, and so forth. That's obvious to us, but maybe not obvious to other people.
Yeah. So it is slightly tangential, but when I say Ricci of the connection, these connections don't satisfy the Bianchi identity, right? So you can take different traces of the curvature tensor to get different Riccis. Anyway, so what was this? Okay, so we have this line, and I've justified it by saying this is the line that generalizes Kähler's geometry, right? This reduces to the Levi-Civita connection when the metric is Kähler, which is certainly a good justification, in my opinion. But what's remarkable is that so many other distinguished connections that have been looked at lie on this line, okay? So, for example, for S equals 1/2, I'll call this the Lieberman connection. Okay. This has the property that the torsion satisfies the Bianchi identity. Okay. So it's another condition, sort of dual to this one, right? Dual in a very imprecise sense, but similar to that one. But there's more. If I take S equals to 2/3, this is sometimes called nabla min. Okay, we call this the minimal connection. Okay, so this has the property that its torsion is minimal amongst all Hermitian connections. Okay. One more is nabla 1. Okay, and we call this the Lichnerowicz connection. Okay, and this is the projection onto the space of Hermitian connections of the Levi-Civita connection. Okay, so you can draw a cute little line. If you have, so here we have the Churn connection corresponding to 0. This is 1/2 is Lieberman. 2/3 is the minimal. 1 is Lichnerowicz. And 2 is Bismut. Okay, and Levi-Civita for a non-Kähler manifold sits up here. Obviously, in the Kähler case, this is all just a point, but sits up here, and it's the orthogonal projection onto this space. Okay, and as far as I know, these are all the distinguished connections that have been studied in Hermitian geometry. I should note this also extends to almost Hermitian geometry, but I won't consider that case. But you can do the same construction. So yeah, it's quite remarkable that this line, just, you know, the span of the Chern and the Bismut connection considered in this affine space gives you the, like, all these distinguished connections. Okay. All right. So let me just make a very quick remark that the holonomy of a Hermitian connection is always in UN, right? Okay, and this is why, you know, if the Levi-Civita connection has holonomy in UN, this is equivalent to being Kähler, right? So this is because essentially that if we take the directional derivative and compose that with J, it commutes with J, okay? And so we have this holonomy always sitting inside a UN group. And so Yao asked this question in the 90s. This. So which compact Hermitian manifolds admit some Hermitian connection with holonomy, a proper subgroup of UN? Okay, so what is like kind of the metrics which have a special holonomy with respect to these connections? Okay, so in particular, so this wasn't directly asked by Yao, but it's a more refined question, which admit flat Hermitian connections. Okay, so we say nabla is flat if its curvature tensor vanishes, right? So 0 is the curvature tensor, and this is literally just how we define it for the Levi-Civita connection, just like that. I guess we want x and y in the tangent. All right, so it's a natural question, right? So if I take some Hermitian connection, say it's flat, can I say anything about the manifold? Obviously, for the Levi-Civita connection, this is very easy, well, relatively easy. It's a torus, right? Or covered by a torus. So this has been answered over the years for a few of the distinguished Hermitian connections that I mentioned, right? So let's just take a manifold to be compact, and let's just consider the universal cover. Okay, so this is just notation. This is the universal cover. Okay, if the Churn connection, which remember is just the kind of origin of our line, if this is flat, then it's a result of Boothby that it's covered by a complex Lie group. So the universal cover is a Lie group, has a Lie group structure. The complex structure, when we lift it, is bi-invariant. And the Riemannian metric is left invariant. Okay. So recall, if you have a real Lie group and a bi-invariant complex structure on it, we call that a complex Lie group. So this is a group with a complex manifold structure for which the group operations are holomorphic. Okay. So this was a result of Boothby in the 50s. In 58, I believe, yes. So that's for the Churn connection. You can get a similar result for the Bismut connection. So if the bismuth is flat, then what do we get? Well, again, we actually get that the universal cover is a Lie group. The lift of J is now no longer bi-invariant necessarily, it's a left invariant. But now the metric G is bi-invariant. Okay, so notice that for Chern flat, we had J bi-invariant. Maybe I'll do this in red. J was bi-invariant and G was left invariant. But then you look at the other distinguished connection, the bismuth, the roles switch. Left is J and J is left invariant, but now G is bi-invariant on this Lie group. And this was done more recently by Yang, Wang, and Zheng. This was done in 2016. Okay, and I should mention that this case also covers it also essentially covers the non-compact. So this result also holds for the non-compact case. When it's non-complete, you have to specify that the cover is an open submanifold of the Lie group. But this is getting a bit too technical, but it seems you can drop compactness here. You can't drop compactness for this one. There are counterexamples, okay? So interesting, right? So we got model spaces for the Churn connection, which are complex Lie groups, and model spaces for the Bismut connection, which are Lie groups with a left invariant complex structure, but bi-invariant metric. So remember, if a Lie group has a bi-invariant metric, then it's isomorphic to a product of a compact Lie group and Euclidean space, right? So one can imagine, like, if we have kind of an interpolation of this, right? You know, if we have some other Gauduchon connection, so some other connection on this line being flat, how's this going to interplay, right? This complex Lie group structure and this bi-invariant metric, it's probably going to be quite rigid, okay? Before I get to that, I want to be able to state the main conjecture we were looking at. I need to introduce one more very quick definition. So apart from looking at flat metrics, we could look at metrics whose curvature tensors have the same symmetries as that of a Kähler metric. So we say this is Kähler-like, which I'll abbreviate KL, if one, it satisfies the Bianchi identity. Okay, this is satisfied by, you know, the Riemannian curvature tensor. And so we ask if there exists some Hermitian metric which satisfies that. And also there's a type condition, right? So we want kind of the first two entries to be Hermitian, like this. We'll call this the type condition. This is for X, Y, Z, Tn. Okay, so sorry, this should be equal to 0, right? So we ask it to satisfy the Bianchi identity and this type condition. And that's because these two conditions are precisely satisfied by Kähler metric, by the Levi-Civita connection of a Kähler metric, okay? And notice that if it's flat, then it's Kähler-like, right? If this is 0, then that's 0, and this is 0, this is 0, then it's trivial, okay? So this is a more general condition to study. So one can also ask what happens if Hermitian metrics are Kähler-like. So finally, we can state the conjecture that we're interested in. And so this is attributed to quite a few people. This is by Yang and Zheng in 2018. But I'm also going to include Angela, Hotel, Fugata, and Villacampa, also in 2018. The reason I've got two different sets of names will become clear in a second. Compact emission manifolds with scalar-like say nabla S are scalar for S not equal to 0 or 2. Okay, and the reason there's two sets of names is because Yang and Zheng conjectured this first for the flat case. Okay, but you can see that this conjecture itself does contain the flat case. So it's an interesting problem, right? So if we ask that a Gauduchon connection nabla S has the same symmetries as that of a scalar metric, then we claim that the metric itself is scalar. Okay, but we ask S is not equal to 0 or 2, obviously because these two examples have been covered here. So these are plenty of non-scalar examples. I forgot to mention that. Plenty of non-scalar examples contained in these two cases, right? But for the rest, we claim we expect it to be scalar. Okay. So is there any questions on the statement of the conjecture before I talk about some work that's been done? Okay, good. So here's a very, I don't know, stress non-exhaustive list of previous results on this. If M is complex three-dimensional, i.e. real six-dimensional, and it's a solved manifold, meaning it's a compact quotient of a solvable Lie group, and its trivial, and its canonical bundle is trivial, which means it admits a nowhere vanishing holomorphic volume form. Then the conjecture holds. I'll just give it a tick. Okay, this was done by again Angela, Hotel, Ugata, and Villacamp. In the same paper, they conjectured to be true in general. Yep. So if nabla S is flat and n equals 2, so this is complex. Maybe I'll say dim. M equals 4, so complex dimension 2. Then it holds. This was covered by Yang and Zheng in 2018. If it's scalar-like, and now we impose a condition on S, okay, and so this is it's a very strange interval, but if S is not inside this interval, so we got 4 minus 2 root 3 and 4 plus 2 root 3. We also don't want it to be 0 because that's the Churn case. This is 0.54, this is 7.46 roughly. Then it holds. So there's a very strange, mysterious interval for which it's possibly open. So this was done by Yang and Zheng in 18 for the flat case, and then Zhao and Zheng in 2021 for the scalar-like case. So this is done for the flat. Okay. Further to this, the same problem's been studied with some symmetry assumptions. So if you take nabla S flat and say M is a Lie group, not necessarily compact, and say the dimension of M is 4, or the torsion's parallel, then it holds it again. So this is done by Vizzoni, Yang, and Zheng in 2019. Okay. This is not strictly part of the conjecture, but it's interesting to note that the Bismut connection is Kähler-like if and only if G is pluriclosed, sometimes called SKT, and the torsion's parallel. Okay, so this was a result by Zhao and Zheng in 2019. Okay, so pluriclosed means this omega I defined before is DD bar closed. Okay, so remember omega is G, and we ask this form is DD bar closed. So that's interesting. And then again, not really a result, but I'll mention that there's no non-trivial compact Chern Kähler-like examples. Examples known. Okay, there's some non-compact ones known, but yeah, the compact case is open. It would be interesting to find some examples in that case. Okay. I guess I should state my main theorem now. So we showed that
you had a question from the chat there, James.
Oh, really? Excellent. Oh, sorry. Yeah, non-trivial means non-Chern flat and non-Kähler.
Do you remember the example?
The
non-compact
compact example?
No, the compact one.
Oh, the hop surface. Wait, what?
Churn,
I'm confused what you're talking about.
The Churn Kähler-like compact complex example. You only know one. Do you remember?
Are you asking about the one that I thought I found? I haven't told you
No.
that was
the
wrong.
Iwasawa threefold is your favorite example, and that's the example that you're talking about here. That's the only known example of a compact.
But those are Chern flat.
Yes, that's what you mean by non-trivial, right? Is that it's not Chern flat.
I mean an example of non-Chern flat and non-Kähler.
Yeah.
But the Iwasawa is Chern flat.
Is Chern flat, and that's the only example of Chern Kähler-like in the compact case that we know about.
Well,
Right.
I guess any quotient of a complex Lie group also gives you that with a left invariant metric.
Of a
The Chern flat examples are all the quotient are all compact quotients of complex Lie groups with left invariant metrics. So you get abundance there.
Yeah, you're right. You're right. What am I thinking? I'm thinking of Chern Kähler-like. There are no non-flat ones in the compact case. There's not a known example, right?
Yeah. Yeah. Exactly.
Yeah. Okay. That probably doesn't help anyone else except for you and me. But
That's all right. Thanks for the question. So yeah, our theorem that has recently been uploaded to the archive. So if we have a Hermitian manifold, okay, and then if so notice I'm not assuming compactness here. If nabla S is Kähler-like and S is not equal to 0 or 2, so again we're excluding the Chern and Bismut cases, and either, okay, so I mean we can assume M is compact, or we can assume it's non-compact, but S is not equal to, say, these two values. Then MJG is K. Okay, so in particular, we prove the conjecture. And we also almost get it for the non-compact case, except for two values. Okay. Moreover, we have this corollary. And this is a corollary of the proof. It's not of the statement, but our method of proof. So, the compactness assumption, we really only use it to show that a certain function attains its maximum, and then we argue from there, right? So the compactness is not so essential. Say we have a group acting on our emission manifold such that its orbit space, right, or its fundamental domain is compact, then the same holds. Okay, so in particular, it holds when the orbit space is just a point. Okay, so it's a homogeneous manifold. Okay. So this means finding examples for this case is going to be kind of annoying, right? Any symmetry assumptions you impose that it can't have a compact fundamental domain. So it's a little tricky. Let me just recall. So you're probably wondering why these two numbers, right? Nabla 2 on 3 is the minimal connection. Okay, and we don't know any interpretation for S equals 4 on 5. This is quite mysterious. It would be great to find some non-compact, Kähler-like or flat examples for these two connections, but so far we've been unsuccessful. And again, looking for these examples, as I said, you can't assume homogeneity. If it's cohomogeneity 1, maybe, but it can't have a compact quotient, so it's tricky. Did anyone have any questions on the statement of the theorem? All right. So I'll probably spend a little bit of time discussing the proof. So at its heart, it's quite straightforward. It basically comes down to solving this linear system for a few functions that we define. So let me just try and perhaps give some intuition into how these Kähler-like conditions allows us to do that. So just by way of notation, let's just denote the torsion by Ts. And let's just call T without any S the Churn torsion, right? So I want this to be the torsion for S equals 0. And it's helpful just to always work in terms of the Churn torsion because it's got very nice expressions in components and allows us to do quite a lot. Again, we'll just following that, we'll just call RS the curvature of Nabla S, okay? So let's complexify everything. So we take the tangent bundle and we tensor it with C, okay? And then I'll extend all maps and tensors by complex linearity, okay? We decompose this into two sub-bundles. And these are just the plus I and minus I eigenbundles of J. So we've got J on T10, so I guess it's T10 T01. J on T10 is plus I, and J on T01 is minus I. Okay. Let's take EI from I equals 1 to N. This is going to be a local frame. This is a local unitary frame. Okay, so it's a set of complexified vector fields in the plus I eigenbundle, and it satisfies this. This is what it means to be unitary. We just want it to be, you know, orthonormal sort of at every point, right? If we raise the index on these, okay, then we'll call that the dual frame. Okay. And then one component of the torsion, the Chern torsion, that's going to be very, very helpful to us is what we call the Torsion One Form. So this is just the trace of the torsion. So we take, by convention, we'll take a half. We'll sum from I equals 1 to N. We'll take the torsion, and we'll leave the second slot of the torsion open, and we'll trace over the first slot. Okay, so this is the Torsion One Form, sometimes called the Gauduchon one. Okay. So that's just notation, some setup. Now we get into the actual the argument of the proof. So the definition of nabla S, okay, so you fiddle around with that. It means that you can write the torsion TS as some linear expression in the torsion of the Churn connection, right? So this is linear in T. Okay, so for example, if I evaluate this on the vectors EI, EJ, then this is 1 minus S T EI EJ. Just go check, yeah, S equals 0, it agrees, okay? So that's, for example, that's the case, and then you have another formula when 1 is kind of a bar, you know, because you've got to cover the whole T10 plus T01, you have different formulas, okay? But the point is you can write it in terms of the Churn connection. Now, how are we going to use the Kähler-like condition or the flatness condition, right? Well, we have this Bianchi identity for general connections, right? So if we take the cyclic sum of this quantity, then normally Bianchi would mean, like for Levi-Civita, this would be 0, okay? But here we have a complicated expression in the torsion and its derivatives, right? So we have this term, which involves covariant derivatives of the torsion, plus another term which involves this quadratic term in the torsion. Okay, so Kähler-like, what does Kähler-like mean? Well, remember, Kähler-like means the curvature satisfies the Bianchi. So the left-hand side is 0. Okay, and you play some tricks with the symmetries and the vanishing of certain components of torsion. We know that TS can be written in terms of T. Ultimately, what this gives us is a formula for the covariant derivative, so the S covariant derivative of T in terms of T itself. So this is quadratic. Okay, it's quadratic because we had a quadratic expression there in the Bianchi identity, right? So the idea is left-hand side equals 0, you solve for this in terms of this, okay? So what this tells us is we can reduce derivatives of torsion to algebraic expressions of torsion, which is really, really nice. So for an example of this, it's a contracted example, right? So if I have 2 times 2s minus 1 times, we kind of have this divergence of this torsion one form, right? So we've contracted this. This is s squared times the norm of the torsion squared plus s times 2 minus 3s times the norm of eta squared. So this is an important example, which I deliberately told you about, because if, say, eta was 0 and s was not equal to 0, or say s was a half, then then this would mean that the torsion must vanish identically, which would imply Taylor. So why is that, right? So say eta was 0, then this side would vanish, this would vanish, and then the torsion has to vanish for s not equal to 0, right? Say s was a half, then this side would vanish, this would be bigger than 0, and this would be bigger than 0. Again, these two have to vanish identically, right? And then the torsion vanishing means that the Churn connection is the Levi-Civita connection, which means it's scalar. Okay, so this was first observed by Yang and Zheng in 2018. Right, so this was stuff that had already been observed. You can get these formulas for the covariant derivatives. How are you going to use the Kähler-like condition? Tim, do I have 5 minutes, right?
Yeah, you can keep doing that.
Yeah, okay. So I'll try and do a quick overview in the last 5 minutes. There's my notes, there they are. So the idea we had was basically we look at no longer looking at first order computations, we have to go to second order, okay? And of course, second order, second derivatives, curvature, symmetries of the curvature, maybe we can gain some information this way, right? So the idea was to look at second order. So remember, we can write the curvature. So this curvature, this is an endomorphism, right? In general, we can write it in terms of the second covariant derivatives. It's this commutator. But this isn't a Levi-Civita connection, right? We normally have a torsion term hiding there. This is not so bad though, because we know what derivatives of torsion are, right? So what does this tell us? Well, that tells us that if we apply the curvature to T, our torsion, well, this gives us some cubic expression. Okay, it's cubic because we're taking second derivatives of T and we're applying the product rule, so we get a nice cubic expression. Well, it's not nice. This is quite a lengthy, you know, when we do these computations, they're very, very lengthy. So the idea is to consider contractions of, well, we take the third tensor power of T and then we tensor it with eta. Okay, we have A, B, C. We have 3 functions, right? The only important one is this C because it's the norm of this torsion with eta inside, and then it's got the open slot, and these are all complex functions. Okay, right. So we consider these contractions of this, right? Why do we care about that? Well, contractions. So we take the contractions of, say, this curvature tensor. Well, this tensor. And we use the Kähler-like symmetries. Well, this actually gives us a linear system for A, B, C, and one other function, which is this first order function here. Okay. So I won't go into actually applying this, but you take contractions of this, you apply the Kähler-like symmetries, and you get 4 equations. Okay, so you end up with this matrix. You get lambda, which depends on S, times the vector A, B, C, times this first order function. And this has to be 0. Okay, so this is a 4x4 matrix. And the determinant is a very high order polynomial, but it factorizes very, very nicely. This is quite remarkable. It took us quite a few goes to get this factorization, but it eventually happened. And you get all our friends from the distinguished, from the Gauduchon line showing up. I'm running out of space to write this polynomial, but we continue. 3s minus 2 squared times 5s minus 4. Okay. Now, this is the only bit of analysis in the entire talk. If M is compact, well, that means that eta squared attains a max at some point P. Okay. Well, this means, first of all, that this last term is 0. Okay, right? So this is 0. And so that essentially means that the system is overdetermined. Okay, so it's now a 4x3 system instead of a 4x4. You have to be careful to make sure that the rank isn't so low, but the rank is high enough to conclude that C equals 0. Okay. Well, if C equals 0, that means that T of eta sharp bar, because it was the norm of this, is 0. If you take the trace of this, you get norm of eta squared equals 0. And because it was a maximum, eta is 0 everywhere. Okay. And then that proves the theorem because of what I mentioned before, eta being 0 gives us what we want. And so for M non-compact, okay. Well, N non-compact is not so bad because as long as this determinant is non-zero, A, B, C, and this other term will all identically vanish anyway, right? So the determinant is not equal to 0 for S not equal to 0, 1/2, 2/3, 4/5, 1 or 2. Okay, these cases have been covered. This can be covered by by Yang and Zheng, because this case implies that eta equals 0 already, and so we're left with these two cases, which we're not quite sure what to do with. Okay, but that's essentially proof because you know, this implies C equals 0, and you do the same thing as before. Okay, so that's the proof summary. Hopefully that was somewhat enlightening. But yeah, I'll leave it there. Thank you.
Tim, your mic is on if you're talking. No, you're not. Oh, okay. Your name covers your mouth as well. James, can I see the second order functions?
Yeah. Can you still see my screen? Did I stop sharing?
No, you stopped sharing.
Oh, sorry. That didn't happen halfway through the talk, did it?
No, yeah, the whole talk was fine.
Good. Okay, sorry. Which were we talking about?
You said like you considered these second order things, yes, not first order things.
Yeah. Mm-hmm.
Because it's a okay, so it's yeah, okay. How close is it to you know, Boothby's argument, where to show, for instance, that you know, the Chern flat, it's a Bochner argument applied to the norm squared of this. which looks somewhat similar to what's going on here. Have you thought about?
So originally this was very similar to Boothby's argument, but obviously Boothby's argument only works in the compact case. Now I would say it's quite dissimilar. We don't employ a Blochner formula. There's no Laplacian involved. It's all very local. Really, the only point we use compactness is that this eta, this norm of eta, attains a maximum. Okay, so
maybe that could extend the results for constant Chern holomorphic sectional curvature implying Kähler, because that's the technique used to.
Yeah,
that would be interesting, because if you're avoiding the Blochner technique, that would be very interesting.
Yeah.
What is the dual of the 4/5? Do you happen to know the number?
It might be. Oh, you mean the dual in the sense of
in any sense that's been proposed by the number of people who do this?
I can't remember. I think my memory is telling me it might be -1 or something. I can't. Yeah, I'm not sure. Yeah, I really don't know this 4/5. It's very mysterious. 2/3 makes sense. I wouldn't be surprised, if there were examples. I mean, I say that, but it's just because it's got a name, right? But 4/5 doesn't have a name, so I don't know.
That's the Lafuente Stanfield
that's
connection.
this.
So but you get this from the vanity of the determinant, but it must reflect a zero eigen direction. Have you looked at actually trying to solve the system and working out what that direction corresponds to? Or
you mean in these two remaining cases? Yeah. So
no, well, particularly the 4. You have this mysterious 4/5 and I guess 2/3 as well, right?
Yeah. I have done that. So what you get in the remaining case, basically the system reduces to, I think for 2/3, it's something like B equals C equals, I don't know, like 4/15 of this guy. And something similar for 4/5. So it's rank 1 or 2 in those cases. So this is basically all the information you get out of it. You can conclude some things from it, but it wasn't enough to conclude Kähler. I don't know.
Is there any hope of constructing examples?
I've looked at C2 with like a cohomogeneity 1 action and checked these necessary conditions, but they failed pretty quickly. Beyond that, I'm not really sure. I'm not really an expert in cohomogeneity 1 stuff. So, but you'd want to, I think, the obvious place to look is like, actions of G where this is diffeomorphic to say R or maybe the half interval or something. This would be something Tim would probably love to look at, but I don't know. Because obviously if it's the circle, if it's cohomogeneity 1 action and it's a circle, then you can't say anything because it's compact. Same with the closed interval. So if it's got symmetries, it's got to be sufficiently bad for the quotient to be non-compact. The argument in that case, if it's got a compact quotient, then again, this is attaining a maximum. So you really you want to find examples where this isn't attaining any sort of maximum.
How on earth you would come up with such an example?
Yeah, I don't know. They seem easy to cook up for the Chern flat case, but that's because you've got these lovely frames and everything. But as soon as you add this S parameter in, it's pretty wild.
there any subsequent conjectures along this line? Or is this, I guess the holomorphic sectional one is the big one that people want, but did Zheng and anything, like, did they say, like, this is why we want to understand it, and this is, or is it closing the door on the Gauduchon scenario?
Well, obviously the Churn case is still very open. So I think the Churn case is the next place to look in terms of Kähler-like symmetries. It would be very, very interesting to find a compact Churn Kähler-like example that is non-Churn flat and non-Kähler. That's what I would say is the next door.
I would even be happy with the weekly Kähler-like things that we. I actually think those are more. Well, I'm biased because I came up with them. Well, we came up with them, but I think those are more important. Has Yang and Zheng looked at it, spoken to you about it yet, or
not yet?
he probably wouldn't email you. Does anyone have any questions? I forgot that I'm chairing this. Sorry. Why isn't Tim asking if people have questions? Okay, I have another question then. Unfortunately, too close to the field. The relation between Bismut Kähler-like and pluriclosed. So you said it's true if and only if. Is that the statement that the Bismut connection is Kähler-like compact or not compact? Compactness required or not?
I don't think you need compactness now. This is a local statement.
This is the Fino-Tardini thing, isn't it? Is it? Or is this?
Yes, but Zhao and Zheng recently, they've updated the archive a few times, but they've recently proved this.
Like, and it's. Do they produce examples, or they just say this is a?
That's a good question. You're probably more likely to find examples in the Fino-Tardini paper. But yeah, I'm not sure.
Because it'd be interesting to get topological, because maybe this Bismut Kähler-like is easier to obstruct than perhaps pluriclosed is easy to obstruct, and that would generate perhaps topological obstructions. For instance, I still don't know if the hypothetical S6 complex structure has a pluriclosed metric, and maybe it'd be easy to show that it doesn't have a Bismut Kähler-like structure.
Yeah, maybe.
No, I'll stop asking questions. Does anyone else have any?
I think
questions?
if you drop this, no, I don't want to say anything that's really wrong, so I'll probably leave.
Well, sorry, I can't help myself. Have people looked at the Bismut Kähler-like condition, the pluriclosed flow, starting from a Bismut Kähler-like metric or something like this? Has that ever been? That seems like a very natural thing to do.
Was that Fino-Tardini? Did they look at something like that? I'm not sure. Yeah, that's a very good question as well.
You can tell me if I'll leave it. I won't ask any more questions now. I'll leave, give people a chance to.
I appreciate the question.
Okay, then. So if no one else has any questions, let's thank the speaker again for the lovely talk. And we resume next fortnight, or yeah.
Yep, that's right. Next fortnight, the plan is to have Jack Thompson give a talk. We'll send out an email with the exact time and the day in due course. I'll stop recording now then. Thanks, everyone.
Thank you.